In the last lecture, we derived the force balance equation for flow in a cylindrical pipe. Now let's look at the case that if the fluid is Newtonian, what can we do with it? And once you have you know that it's Newtonian flow, you basically know the constitutive relation. So when we talk about the constitutive relation, constitutive relation is in fluid mechanics is the shear stress versus shear rate. So Newtonian fluid means tau equal to mu multiplied by gamma dot. And then a constitutive relation plus force balance, which we derived the last time, these two pieces of information will give you a velocity profile. So we have force balance and the constitutive relation. This will help us to get velocity profile. And then once you have velocity profile, you can do a lot of things with it. So in this lecture, we will use Newtonian fluid as a helpful example for us to see this process. How do we get to the profile? Okay, so let's still think about a pipe. Axial direction is Z. Last time I used X, now this time let's use Z. It doesn't really matter, it's just how you call it. It's R. And the shear stress, tau RZ equals to R divided by 2 dP dz. If you forgot about this, make sure you go back to the last lecture and review how we derived this. Now for Newtonian fluid, we know that the constitutive relation tells us tau RZ equals to mu gamma dot equals to mu d vz dr. So these two terms must be the same because both are shear stress. So that means we have mu dvz r equals to r divided by 2 dp dz. So equation may look like a little bit intimidating because you have derivative on the two ends of the equation, and they are different things. You have pressure, and you have velocity, and you have r and z. It looks like it's harder to handle. But if you look at this carefully, if you rearrange it, you will get mu. Let's divide it both sides by r. dbc dr equals to 1 over 2 dp dz. So the pressure is a function of axial direction because it's we say that it's a pressure-driven flow equal P naught at the inlet and the PL at the outlet. And then there's a pressure difference. So pressure is a function of Z, and it's not a function of R because at each cross section, the pressure would be constant. If it's not constant, then you would have fluid motion along the radial direction, which isn't the case for this type of fluid. So now you have VZ is dz is a function of r, and p is a function of z. Now you can look at this equation on the left-hand side. It's a function in r. The right-hand side is a function z. So it's a r and z are the coordinates along two different directions. You cannot have two functions which like vary over r and z and make them equal. That's impossible. So the only thing that can happen is they equal to a constant. So this is a constant. It's a constant also means dp dz is a constant. So to tell us dp dz constant, to tell us p is linear in z. So this is actually a pretty good result for pipe flow. For laminar pipe flow, if the flow is driven by pressure, then the pressure is linear along the axial direction. Now, when you look at this equation again, you can just treat dp dz as a number. You can call it anything. You can call it a, b, c, d, whatever you feel comfortable. And in this case, if you just ignore it's a derivative, you just replace it as a number in your mind, then this is something actually not so intimidating. It's definitely solvable. So you can rearrange this equation to solve for Vz. So let's rearrange this equation. Get d Vz dr equals to r divided by 2 mu dp dz. So you can integrate it. You can integrate both sides with respect to r and integrate. It gives you Vz as a function of r equals to 1 over 4 mu dp dz r squared plus c. C is a constant of integration. This is a constant integration. You will determine constant of integration in this context by the boundary condition. Because it's spatial derivative, it's dv dr, so it's derivative with respect to r. So the boundary condition, so you need a boundary condition. At r position. So the boundary is at the boundary of r. So you look at this problem, you know that due to the non-slip boundary condition, so non-slip boundary condition, and we know that at r equal to capital R, Vz r equal to 0. This will help us to determine what is C. So you plug in, you get Vz r equal to 0 equal to 1 over 4 mu dp dz r squared plus c. We can solve for c. C equals to minus 1 over 4 mu dp dz r squared. So you put the C back, you can get the expression of our velocity, Vz, as a function of r, is 1/4 mu dp little r squared and minus capital R squared. Sometimes people would like to take out the capital R's. So it is R squared divided by 4 mu dp z R squared minus 1. I have some issue with my pen. R squared. Okay, so this is the expression. So we can see that it is quadratic in R, or it's a parabolic. So it's a parabolic distribution. You can check that at R equal to capital R, it is indeed 0. So you always do sanity check after you have solved your equations, so that it makes sense. So how does this look like? So this is your pipe. With R. And if you look at from the side, you would see that the velocity profile look like this. This is how how Vz as a function of R look like. So it reaches maximum at the center line. So Vmax, velocity at R equal to 0, minus 1/4 mu dp dv R squared. You may wonder, like, why it's negative? Because you see that if there's a pipe flow, if it's pressure driven, have high pressure here, low pressure there, in 0 larger than PL, you expect flow along that direction, along the positive Z direction. Well, why you get a negative sign? And think about it. I would like to leave it something for you to think about it. It's not because the equation is wrong, the equation is correct. And it indeed should flow to the right-hand side. And why is that? Okay, now if you have Vmax, then you also have, you can rewrite your V, C, the function in terms of Vmax. You can like replace this term, or like replace dp dr with Vmax into the velocity expression. Then you will get V is equal to Vmax 1 minus R squared. Little R squared divided by capital R squared. I need to give you a clear view how the parabolic profile look like. Okay, we obtained our velocity profile for a cylindrical pipe. So this, let's make clear in underwater situation this is valid. So we derived this equation by using the constitutive law of a Newtonian fluid. So this parabolic distribution is for a Newtonian fluid. Second is we have always assumed that the flow is laminar. If it's turbulent flow, it's something totally different. So it's also laminar flow. So these are the things you need to keep in mind. Of course, this is in a cylindrical pipe. If it's not a cylindrical pipe, you would have something different. So don't misuse this equation. I found that in the past, students would like just blindly remember this equation and use it in all scenarios. Don't do that. This equation, you need to know where it comes from and under what conditions it is applicable. Okay, now let's continue our discussion. Since we have the velocity profile, let's find out what is volumetric flow rate. Volumetric flow rate is the volume flow rate over the entire cross section. So if you look at the cross section, if you look from the side, the radius is r, and on the boundary, because of non-stable boundary condition, the flow velocity is 0. But at the center, it has V maximum. And from the center to the boundary, the velocity decrease in a parabolic fashion. We just derived it. Now, if you want to know what's the volume flow rate across the entire cross-sectional area, you know that you cannot just multiply velocity by area. If the velocity is a constant over this cross-sectional area, then you can just multiply velocity by the area. But it's not a constant, so you cannot do that. And the way you need to handle it is to do integration. So what you're going to do is you take each strip of your infinitesimal element. So you say that each strip has the inner radius is r, and the thickness is dr. But the dr is very, very small. It's infinitesimally small. So now for an extremely small band of region, you can approximate the velocity as a constant. That's the spirit of calculus. So you divide the domain into infinitesimal portion, and within each infinitesimal region, you assume some quantities being a constant, and then you can do integration over the entire domain. So now for this small element, let's call it the volumetric flow through this ring. Let's call it dq. Okay, now dq equals area multiplied by velocity. The area of this ring is 2I r dr, and the velocity is vz. So the vz we just derived it above there. It's a quadratic equation. Now, if you want to, well, let's rewrite it in a more suggestive way. So you can write it this way: 2I r vz dr. Now, if you want to find the total Q, what you need to do, you integrate over all the dq's, it means you integrate over the entire domain, which is R from 0 to capital R. Now, if you plug in the expression of VZ and you work step by step, you will get the expression minus pi r squared, sorry, pi r to the power of 4th divided by 8 mu dp dz. It's clear, it's power of 4. Now the middle steps I have skipped. This is left as an exercise for your homework problem. So exercise or homework. Complete the middle steps. In the integration. Okay, now these don't look friendly because you still have derivative, and sometimes people are afraid of looking at the derivative. And there's also a minus sign. So let's fix this. We know that the pressure is linear. So if it's linear, it's easier to handle. We know that the dp dz would just be the pressure at L minus pressure at the outlet minus the pressure at the inlet divided by the length of the pipe. This is only true if it's linear. If it's not linear, you cannot like calculate the derivative in this. So if it's linear, you can do this. So it is minus delta P divided by L. Recall that delta P is defined as the pressure drop across the, this is the pressure drop. So now we can rewrite our Q in a nicer way. Pi r the power of 4th divided by 8 mu L delta P. This is an equation which we call the Hagen-Poiseuille equation. Sometimes we just call it the Poiseuille equation. This relates Q to delta P for a Newtonian laminar flow in a cylindrical pipe. Relates Q to delta P for a Newtonian laminar flow in a cylindrical pipe. So Q is volumetric flow rate, delta P is pressure drop. And now let's just have a quick mention why it's related to the capillary viscometer we mentioned earlier. You can see that Q is something you can measure, delta P is something you set up, and then you know the dimension, you know R and L of the pipe. So that's how you can use this relation to find the viscosity of the fluid. So if it's a Newtonian fluid, you can just run a flow across like a capillary pipe, and then you can just estimate the viscosity. It's a pretty neat method. Okay, now we just look at the volumetric flow rate. Let's look at average velocity. Average velocity means, well, we just discussed that the velocity over this cross-sectional area, it's not a constant, it's a function. Bz is a function of r. So it's a maximum in the center and a zero on the boundary. Now, if you ask what's the average velocity, because average velocity is something like in biomedical engineering or in the industry or any practical applications, people would like to ask what's the average velocity. They may not necessarily ask how the parabolic profile look like. They want to know on average how fast fluid flow across the pipe. That's all they want to know. So by definition, the average velocity is the volumetric flow rate divided by the cross-sectional area. And in our case, we have the average is, what is Q? Q is I R force delta P 8 mu L. And then divided by area, area is I R squared. So it gives us R squared delta P divided by 8 mu L. And if you compare it with the maximum velocity we just derived, the maximum this expression, you will find that it equals to, it happens to be 1/2 V maximum. This is just because of the parabolic feature and for this cylindrical geometry. If it's not like this type of flow, if it's for example, if it's not a circular cross-sectional area, if it's not a Newtonian flow, or it's something else, then you probably don't get 1/2 maximum. So a lot of students would misunderstood the average velocity. They thought, okay, the average would just be the maximum plus minimum divided by 2. That's why 1/2 maximum. That's not the reason why it's 1/2 maximum. This 1/2 maximum, you should always calculate average velocity from these. This is the definition. And it happened to be 1/2 maximum for this particular problem. So I cannot emphasize more. In the past, the students always make a mistake. They always think that for any flow, any geometry, it's 1/2 maximum. No, that's not the case. Okay. Now, you can also calculate the wall shear stress in terms of like the V maximum or average or whatever. So since the wall shear stress, last time we discussed it's R divided by 2 dP dz. So if you convert it into delta P, it gives you minus R divided by 2L delta P. Now you may ask, well, why is it negative? R is positive, L is positive, delta P is also positive because we set up a pressure difference to drive the flow. So indeed, the wall shear stress is negative. And actually, all shear stress in this scenario, in the pipe flow, the shear stress, by the convention of the sign convention of shear stress, it is a negative shear stress in a sense that the shear stress, if you, once again, draw this, if you take a control volume, and then you ask, what's the shear stress acting on this surface, the shaded surface on the side? So the shear stress would be defined by the stress on the surface that has positive direction defined by our coordinate. And in this case, a negative shear stress means the surface of the flow of this control volume actually feel a negative force. It is a drag. The reason is if you think the layers of fluid, the layers are close to the boundary is has low velocity. Actually, at the boundary, it has zero velocity because of non-slip boundary conditions. And when it's getting closer to the center, the velocity increases. So that means the fluid layer close to the wall tends to move slower than the fluid at the center. Then it tends to sort of hold back, provide a viscous drag to the fluid which is close to the center. And that's why the shear stress is actually along the negative direction, or is negative. Okay, so if you like rearrange these equations, you can find that the tau W, the wall shear stress, is minus 4 mu r average velocity. It's also minus 2 mu divided by r of the V maximum. You can find these pretty easily. You just rearrange these equations. Now, if you ask what is the wall shear rate, so tau W is wall shear stress. And if you ask what is wall shear rate, gamma dot W. And to find this, you use the Newtonian constitutive relation. Means if tau is mu multiplied by gamma dot, then gamma dot is tau divided by mu. So now you know it's minus 4 divided by r, the average. Again, this is only valid for a cylindrical pipe. Don't apply it to other pipes. It doesn't work in that way. And the good thing about express wall shear stress in terms of average velocity is that you can now think about the size of the pipe and the average velocity. And you only need these two information to tell you what is wall shear stress. So this gives you a quick way of like estimating wall shear stress in a, for example, in a application or industrial setting if you want to know this number in a cylindrical pipe. And for this reason, if you are only looking at like the ratio between average velocity and the size of the pipe, sometimes you may want to have some scaling factor. You may say, okay, what if the velocity increase, but the pipe size, the size of the pipe also increase? Does that change the wall shear rate? If you as you can see from this equation, if both average velocity and r, the size of the pipe, doubles, the wall shear rate doesn't change, it remains the same. So to give you some feeling of scaling factors. And so people sometimes would like to define something for the reduced average velocity to account for the ratio effect. So let me just define what is reduced average velocity. I put a question mark. I put a quotation mark on velocity because it's not really a velocity. You can check the dimension. It's not the dimension of velocity, but people just call it. We got the U bar defined as V average divided by the diameter. So B equal to the diameter of the pipe. And if you define this reduced velocity, average velocity, then you can express the wall shear rate as minus 8 mu r. So it gives you a ratio so that you can directly relate the washer rate to this ratio, to this so-called reduced average velocity. This is why it can be handy in some industry application. Let's look at an example. Have a large artery has a radius of r equal to 0.5 centimeter, and the average blood velocity is the average equal to 40 centimeter per second. Find the washer rate. So this is pretty straightforward. You can just directly use this equation. So this example isn't anything challenging. It helps you to build the feeling or like intuition of using those equations. Sometimes a better way to develop intuitions of equations is to use this when you solve problems. So we have washer rate, gamma W is minus R, V average with minus 4. The velocity is 0.4 meter per second. The radius is 5 times 10 to the minus 3 meter. It gives you minus 320 seconds. That's the washer rate. Okay. Now let me leave an exercise for you. So the exercise is a Newtonian liquid flows through a horizontal cylindrical pipe. The radius of the pipe is given, 0.25 centimeter, and the length of the pipe is also given. So the pressure drop across the tube is also given. It's 3,000 pascal. The volumetric flow, somehow they measured it to be this value. Then find the viscosity of the fluid. So this is an application of capillary viscometer. So let me just put a note. Application. Capillary viscometer. Before we wrap up, let's have a quick mention of what happens if you have a rectangular pipe. So if you have a slit, rectangular pipe, so means you have a pipe look like this. The pipe has length L, width W, and height 2h. So height 2h, width W, and the length L. The slit means H is much less than W, and W is much less than L. For this geometry, we would find Q equals to 2WH cubed divided by 3 mu L delta T. The exercise of homework is to derive this relation. Derive this equation for the slit rectangular pipe. As a hint, you will need to use the combination of force balance and the constitutive relation. It's a Newtonian flow. Newtonian flow, laminar. So make sure you review this lecture and the previous lecture. And then after you fully digested the way we derived for the cylindrical pipe, and then work on this one.